I'm going to talk today about some joint work with a former PhD. No, well, he's yet to graduate to do his viva, but this is the body of his doctoral thesis. Is Edwin Fong, who's now in Copenhagen with the pharmaceutical company Novo Nordisk, and also Stephen Walker, who's professor at UT Austin, and it's around an area called Bayesian predictive inference, something I've been kind of interested in for some time. And I'll give you this kind of one kind of height, the yin and the yang of kind of statistics. And so I'm interested in how one goes from good predictive models to being able to make inferential statements about parameters or statistics of interest. And so we know that in machine learning, for example, there's a big focus on prediction. And it always feels like if I have a really accurate predictive model, a prediction model, then that should be able to allow me somehow to go from a good predictive model to being able to make some inferential statements about the population from which the sample, let's say the training data, was joined. So that's what I mean by inference. I mean, being able to make some statistical statements about population parameters or functionals of the population. Now, as we're well known, like if in a Bayesian framework, going between these two is some sense is straightforward, is that if you have an inferential Bayesian model, by definition, it's kind of generative and you can make predictions, and the parameters have inferential meaning. But more generally, are there ways that we can go from good predictive models to kind of statements of inference? And that's what I'll talk about today. And in some sense, it's going kind of back to basics of Bayesian inference. And so I'll talk through the motivation for using prediction as a tool for inference, and some very simple examples before going through more general predictive distributions, relaxing some of the strong Bayesian assumptions, whilst hopefully retaining good properties for inference, and then a couple of examples and then conclusions. Okay, so kind of, Bayes 101, I guess, if I was in the States, is that the way we would teach typically Bayesian statistics or Bayesian inference would be, you would begin with a likelihood function or a model. Formally it's a normalized likelihood function, so it's a full, sampling distribution for the data. And I'm going to use f sub theta to denote that full sampling distribution for the data y, given some set of parameters theta, and a prior which I place on those parameters. And then following a set of data, we can use the famous rule, Bayes' rule, to obtain a posterior distribution, which I'm going to denote pi theta, conditional on the data that you've observed. And it has this, usual form where I've assumed that the likelihood factorizes conditional on theta. And but a very kind of simple question is, if I look at this left-hand side, where is the uncertainty coming from? So we normally would teach this by the update. We'd say you have prior on a set of parameters theta, you observe data, and just through conditional probability, we obtain this left-hand side. But I'm interested in some senses, it's interesting, I think, to ask, this posterior will have a certain spread, let's say, certain precision. Where's the uncertainty coming from? Where does the posterior uncertainty arise from? And what we're going to argue today, what I'm going to argue in this talk, is that it's the missing data. Yeah, it's the data that you didn't observe that is needed to be able to pin down the parameter of interest. And the parameter of interest, I'm going to use theta naught to denote the parameter you would obtain from, say, an estimator, an unbiased estimator, given an infinite amount of data. And I'm going to argue it's really important. It's a bit unusual to kind of view it in this way, but it's important that everybody's on board, that I'm thinking about what would happen if I gave you an infinite data set. And as we know, if the model's regular, this thing on the left-hand side, this posterior, is going to kind of converge around a point. And it's that point, yeah, that I'm going to be kind of interested in. And what we're going to argue is that we're going to make this missing information the kind of the central part of the inference problem. And in fact, all we're going to do is we're going to treat all of Bayesian inference as a missing data problem. And we're going to use tools of imputation. Yeah, and so in a sense, that's almost like the end of the talk, is to say what I'm going to do is I'm going to use imputation tools. And whereas missing data, we would normally have that in somehow kind of inlaid within our data set. I'm missing a covariate value in a particular observation. I'm going to treat the yn plus 1 to infinity as missing data, and I'm going to impute it. And if you can impute it, you can then pick off the parameter of interest. Okay, so as I said, it's really important that we keep some kind of, research question, the reason for doing the inference in mind. You're undertaking this modeling exercise, say, in order to be able to understand a statistic or functional of interest. So we're going to call that the S-demand. So here we have kind of nature's, in some sense, unknown population sampling distribution F0, and I'm interested in some functional under F0. And so that could be, for example, if I was fitting a linear model, rather than assuming that the linear model is true, I can still think about this least squares optimal parameter, the parameter theta that minimizes the population level least squares. Or if I'm fitting a statistical model, a likelihood function, I can think about the population maximum likelihood estimate, the value of theta that indexes the model that minimizes the negative log likelihood under the sampling distribution of the data. And the reason why that's important is that this theta naught has a well-defined meaning, irrespective of the validity of the model or not. So we know the model's wrong, but I can still think about what would happen if I had, in some sense, if I was given the sampling distribution for the data, then I would know the optimal set of parameters for the model. And the statistical uncertainty in theta naught, the value that you care about, flows from the finite nature of the data. Okay, so as I said, the way we're going to try and get to is building imputation models in order to do inference. And Bayesian predictive inference just focuses on the joint predictive, and this is an important part as well. Just to note the word joint in the word here. It's a joint predictive model, P of Y for observables, and we're going to use that as the primary tool for analysis. Now, as you'll all know, we're used to kind of obtaining this object in the conventional Bayesian approach, either through the prior predictive or marginal likelihood, which is the probability for a set of data, say Y, under the prior, where we've integrated the marginal likelihood, integrated under the likelihood, or the posterior predictive, which is what's the prediction for a new datum, yn plus 1, given what we've observed, say, we'll give conditional on a set of observations. And we can write that as a posterior predictive. So here's the posterior distribution, pi of theta, given yn, and this is just the likelihood or the sampling distribution for a new value, given the theta, and we just marginalize. And What we're going to do is we're going to target the left-hand side directly. So we're going to go straight for the joint predictive. And we're going to work backwards. We're going to work from the left-hand side to define a posterior on a theta of interest. And the key thing is that on the left-hand side, that's not indexed on theta. And so we can choose any parameter of interest. Yeah, it could be any statistic from the population once we've got this. So we're going to construct this left-hand side directly. And through that, going from the left-hand side, we're going to construct posterior distributions on any parameters of interest without necessarily going through a likelihood prior construction. And this predictive approach, has its roots in work by Geisser and Roberts and Dave Finetti and others. And would also point out Phil David's work in this area, and particularly in kind of forecasting systems. But the focus here is on inference. I guess that's a distinguishing feature. Okay, so we're going to need a bit of background on the use of the joint joint distribution on observables, and it really is this kind of the starting point for Bayesian statistics. And as many of you will know, if you open up your kind of Bernardo and Smith or theory of Bayesian stats, really the starting point, and from Dave Finetti, the starting point from Bayesian statistics is just simply the specification of a subjective joint distribution on observables for any set, any conditional set and any predictive set. And that's it. I mean, that's what Bayesian statistics is about. It's about specifying that joint distribution. But, as people noted, that's very easy to write down, just to say, well, Bayesian statistics is just the specification of a joint distribution on observables. But actually constructing this, is non-trivial, because I need to construct a joint distribution over all possible outcomes, given all possible conditioning sets. And moreover, given that subjective joint distribution, I then need to I might be interested in other statistics of interest. Like for us, it's a theta, it's a population parameter. And there's a question, how would I use this object above in order to make inference on a parameter of interest theta? And the remarkable thing in Dave Finetti's work is to recognize the challenge and show that how reasonable kind of assumptions of symmetry in this joint distribution lead to a remarkable simplification in the inference task. And so if we restrict our attention to certain forms for this joint distribution, ones that have certain symmetry assumptions, then we're left with a much, much simpler task. And that comes from his famous representation theorem. So, and as many of you will know, is that the underlying assumption is that of exchangeability. So if we have exchangeability in the data generating process, and one way of thinking about exchangeability is that the indices on the data, so if I have y1, y2, y3, if those indices carry no information, and another way of thinking about that is that if you tell me your joint distribution on y1 to n, and you were to permute the indices, you'd retain the same joint distribution over any permutation for any data. So under this assumption of exchangeability, then every joint distribution has this following decomposition, which means, and this is the famous representation theorem, is that for any joint distribution on observables 1 to n has this form of a marginal distribution over something which looks like a likelihood, is a conditionally independent predictive, and a mixing measure, which takes the form of a prior. In Dave Finetti, that's the lurking parameter, the theta. The theta has, in some sense, is artificially constructed. You start from the left-hand side, and say, if I'm willing to assume exchangeability, then I know there exists a factorization of this form. And then the identification of what is this theta? And it has this notion of this kind of lurking parameter, a sufficient statistic for the data in the limit as n goes to infinity. And when we look at the right-hand side, we say, well, this looks like the Fisher's likelihood function that's normalized and a prior, and that motivates the prior and likelihood construction. And moreover, the conditional predictive distribution follows the usual form. So if I'm looking at a predictive distribution given y1 to n, I just have this mixture form, but now over the posterior. And the reason, oh, sorry, I've said that, I've gone the wrong way. Yeah, the reason that's important is that the likelihood and prior is this amazing shortcut in a way. That's the way we think of it, to obtaining the kind of the starting point is the specification of a joint subjective distribution over observables. And the likelihood prior provides a really convenient shortcut to do an inference. And that shortcut through a likelihood prior is so useful, it's updated with Bayes' rule, and it's so useful and powerful that it gave Bayesian statistics its name. In sense of, there's nothing Bayesian, about Bayes' rule. Yeah, it's just when coupled with the representation theorem, it provides this incredibly useful approach to doing inference by conditioning and updating. So in a similar way, de Finetti, you start with a joint distribution, and then through the representation theorem, you see that there's this shortcut, there's this likelihood prior decomposition, which makes inference incredibly easy relative to working with the joint distribution. We're simply going to also look for other shortcuts to working with the joint predictive and overcoming some of the usual difficulties in doing so. So this is going to now tie in with this point that I made about the kind of imputation. So the first question is, if you lay down a conditional predictive distribution, how do I reason about a population parameter of interest? How do I go from a predictive distribution to an inference, an inferential framework? Well, as I said, we can take any statistic or estimand of interest, theta naught, and this doesn't necessarily index a statistical model. It could be the median of a population, for example. Well, just the thought experiment says that if the complete population data was known, if you had an infinite population and you'd observed everybody, yeah, then of course the statistic would be known exactly. There's no uncertainty. There's no statistical uncertainty if I've observed the whole population. If I was interested in what's the effect of a drug in the adult population in the UK, well, if I observed everybody every adult in the UK that took this drug, then there would be no uncertainty. And so, in terms of notation, we're going to think about this theta as an estimator. You can think about it as an estimator for theta naught, unbiased estimate. And as I said, it's the finite nature of the observed data that's the source of the uncertainty. Yeah, by definition. If you get more and more data, then of course your uncertainty, your precision increases. And if in the limit I give you an infinite data, everything is known. There's no statistics to be done. So in which case we can see that the uncertainty flows from the missing data, and let's make that our starting point. So any uncertainty in theta is a consequence of the data that you didn't observe. If I'd observed more data, there'd be less uncertainty. So let's make that missing information the starting point. And we're going to use a joint predictive to impute hypothetical missing data and then pin down the theta. And in this way, this predictive distribution provides a direct characterization of Bayesian inference. So it encodes the uncertainty and the missing information needed to answer the question. Without necessarily using the likelihood and prior. So imputing writing down a joint distribution over n+1 to infinity is challenging, but we're going to take, following Phil David's work, we're going to take a frequential factorization. So we're just going to factorize this left-hand side is a joint distribution. And as we know, any joint distribution can be factorized into a product of marginals. So we're going to take this predictive distribution, and we're going to first of all take a predictive for n+1. Then we're going to condition on that, and we're going to take the predictive for n+2. And so we're going to do this series of kind of one-step predictives. So in order to impute the missings, we're just going to use the very simple recursion, is that we're going to generate a yn+1. So we're going to form a predictive for an additional observation in your training data. I'm going to draw it, and then I'm going to condition on the draw from the model. Okay, this is like really important. It seems a bit odd, is that you're kind of stuffing the predictions back into the model. You know, you're predicting yn+1, then conditioning on that, then predicting a yn+2 and conditioning on that. And if we keep going, we're going to end up with this massive data set. In the limit, we're going to end up with y1 to infinity. And as we said, look, if you give me a massive data set, if you give me that infinite data, I can pin down any parameter of interest. And that's the parameter we're going to pick off. Formally, we're going to pick off a kind of a posterior mean. Okay, now the key thing here is that this yn+1 to infinity is random. Yeah, so the first draw, of course, has a lot of uncertainty because you've only got n data points. And the second draw has probably a bit less uncertainty because you're now conditioning on that. But overall, this draw of yn+1 to infinity is random. And therefore, the theta that you're picking off is random. And the key underlying result from this is a paper by Doob in 1949 on the theory of the application of martingales, which shows that if I use the Bayesian posterior predictive, then this random parameter that I pick off is distributed according to the posterior distribution, your conventional Bayes posterior. So what do I mean by that? I mean, if I construct this using my standard likelihood prior with a marginal posterior predictive, and I run this simulation, I'll get back the posterior distribution. Yeah, so it's another characterization for the posterior distribution, but starting from the posterior predictive. Now, you could rightly argue at this point, it's not much has been gained, has it? You know, I've kind of got my posterior in order to characterize this predictive. And then if I do this kind of weird thing where I predict and I recurse and I predict and update, what I end up with is I end up back at the starting point. But what I will argue, hopefully, is that it's an interesting viewpoint of what Bayesian uncertainty really is. And also it allows for some generalizations. So here's the kind of cartoon, just to kind of make sure that we're all on board. It's worthwhile, I think, thinking about a finite population example. So imagine you were interested in some statistic under the UK population. So N here would be about 66 million or so. And you can imagine that there is, or it's worth imagining that there is some true population data. Yeah. So there's a full population, And each one of those members of the population has values that are of interest to you. Now, when you do a study, say an observational study, what you do is you pick off certain units in this population. So I go and take measurements on 100 individuals in the population. So that would reveal to me 100 rows in this population table, and the rest would be missing. Yeah, I didn't pick off the second individual in this population, and I didn't pick off the third, but I did in my observational study, I picked off the fourth person and so forth. Now, because of exchangeability, I could just reorder those people in my study. So now I think of the conventional where I say, well, I've got data samples 1 to n, here's 2. And the remaining people in that population are unobserved. And what we're going to do here is we're just going to impute the missing population. So if I could predict all of these missings in this data table, then I'd have my statistic of interest. I'd just pick it off, given the full data table. And that would give me one statistic. And now I'm going to do it again in just the same way that we do Monte Carlo sampling. I now make a second imputation because this is unknown. And I get a different population table because it's a probabilistic prediction. And then I get a new statistic. And what I argue, what we show, or what is well known, is that if I do this using a standard Bayesian posterior predictive, and I estimate the parameters of a log likelihood, then you'll get back the posterior distribution under Bayes. So we've seen that imputing the missing data table from a factorized posterior and then estimating the theta returns the conventional Bayes. And by estimating theta, I mean get the maximum likelihood estimate under the complete population. You'll get back the Bayesian posterior. So, what's been gained from all of this extra work of imputing, of filling up these tables, if by filling up the tables, all I am is picking off the maximum likelihood estimate under an increasingly large capital N, then if that just gives me back my Bayes posterior, yeah, it wouldn't be so much of a story. I mean, kind of interesting, yeah, but perhaps, yeah, not overly useful. Well, I think there's some things, it's always interesting to view things from different angles. And so writing Bayesian inference in this way reveals the direct source of the uncertainty in the posterior. All of the uncertainty comes from the missing data. Yeah, because if you had the missing data, there'd be no uncertainty. I think the other interesting thing is that you often hear this kind of comment that says, well, Bayesians treat the parameter as random and the data as fixed, and the frequentist is the other way around. You think of the parameter as fixed and the data as random. And it's never quite, I can see in some sense why you can think of it that way, but it's never quite felt particularly right to me. And I think one interesting aspect of the predictive viewpoint is it makes the Bayes and frequentist distinction very clear. So both of them are interested in the same parameter. We've got a statistic of interest, an estimand, a common estimand. And just if you're a Bayesian statistician or you're a frequent or a non-Bayesian statistician, doesn't change the thing that you're interested in. There's a research question, you convert that into a statistical question, and you have an estimand, and that's what I want to make statements of uncertainty about. And the frequentist statements of uncertainty have the following form. They look at what would happen if I was to repeat the experiment. If I could generate some random y's, n of them, and then use my estimator, yeah, then that characterizes the kind of frequentist uncertainty. Comes from data sets that you might have observed but didn't, of sample size little n. Whereas the Bayes has something that looks pretty similar, but it says, in order to be able to make uncertainty statements about theta, the missing part is not, hypothetical replica experiments. It's about the missing data n+1. So jointly draw that and estimate the theta using that. You could use the same estimator. But here I condition on the data you've seen and plug in the missing. The other thing that comes is the predictive viewpoint changes the nature of the task. From in conventional Bayes, you have to think of a likelihood, or you think of a sampling model and you think of a prior, and you kind of do that together. The task in the predictive inference is to think of a one-step predictive model. Yeah, I need to think of a really good model given a set of data that can make a really good prediction, and I need an update. That's really important because, as I've stressed here, you need a joint distribution. And if you need a joint distribution, I'm going to need a predictive and an update in order to get the joint. And the interesting thing here, of course, is it opens up the use of online machine learning tools. Because if I tell you, I really need a good probabilistic prediction and I need an update, you'd say, well, yeah, actually, maybe there's a lot of tools in machine learning that can give you a good probabilistic prediction. And the continual learning aspect, or the online learning, is that you have to have an efficient update if you're going to run this imputation approach. But more so, it allows you a principled way to relax some of the assumptions of conventional Bayes, as we'll see, and allows for more general predictive machines. So, you know, as we know, Bayesian inference is axiomatic, comes with a lot of assumptions, and that gives you a lot of really nice properties in terms of making rational decisions and coherence. But they come with some strong restrictions, not least of which formally you're never allowed to kind of change your model. And also that the model is true. And so in terms of generalizations, well, here our theta is any population statistic or parameter of interest. It doesn't have to index a likelihood function. It could be a median of a population. We don't have to assume, there's no statements about a true model. We just want accurate predictions in a way. So that the update is not reliant on the notion of being in M closed. And also just to note that computationally, we've changed the task. The challenge here computationally is to be able to predict an update. And just that might be easier or it might be harder, but it's different to actually the computational task in conventional Bayes, dominated by Markov chain Monte Carlo, is to sample a theta from the posterior. You get the theta for free in our approach once you've generated the y, because you just need to optimize an estimating equation or an estimator. Yeah, and that's often easier, but generating imputing the missing y's is the challenge. So it's a different challenge. And essentially what we're swapping is kind of prior elicitation becomes predictive model evaluation. And again, there are different criteria and different strengths and weaknesses in that. Okay, so as I said, we're going to impute this joint distribution over y1 n plus 1 to infinity. Sorry, I've been a bit like, you know, haven't been truly honest, because of course we can't keep going to infinity. What we're going to do is we're going to take a Monte Carlo approximation and actually just go to an n, capital N, that's much bigger than the data you've got and is large enough for you to get small amounts of Monte Carlo error. So, but this is the kind of the nub of it. You've got some data set y1 to little n. You're going to form a predictive, and then you're going to iterate. I'm going to go from little n plus 1 to capital N, where capital N is big. I'm going to generate a predictive sample, and I'm going to stuff that back into my model, and I'm going to update my model, and that's it. And once I've done that a large number of times, I'm going to calculate my statistic of interest using, say, an unbiased estimator, and I'm going to take that as my sample, and I'm going to repeat. And if I do that, and I keep going, and I keep going, and I keep going, I'm going to generate a bag of theta n's, and that's going to represent my uncertainty in the parameter or statistic of interest. So the first thing to note about this algorithm is it's not Bayesian, because it violates coherency arguments about belief updating. I've told you that you're going to specify the predictive given the data set. And that's different to classical Bayes, where you have to specify the predictive before you've seen any data. And once you've done that, you're then on your path, but you're not allowed to touch it. So here we're saying we're going to violate that, and we're just going to allow you to specify your predictive model given everything you currently know. Here's an example just to show you that it does return you, if you didn't believe you, it does return you kind of Bayes if you start with a Bayesian posterior predictive. And what we've done here is taken a very simple normal means problem. So we've got a normal likelihood, which is a generative likelihood with a standard deviation of 1 and an unknown theta, and I put a prior on that. And under this model, we know we've got a closed form for the posterior predictive, which of course is normal. And suppose I'm interested in estimating theta bar, which is a population mean. Well, what I've done here is that we generated some data, and we took the posterior predictive, given, I think there's 50 data points here, and then we generate an n+1, and then update the Bayesian model, and then generate an n+2 and update the Bayesian model. And you get these kind of paths of this mean parameter. And what you see, of course, is you see a lot more variation initially because you're generating, it's like a root n. Obviously, the more information the bigger n is, the less any one particular datum has on the update to theta bar. And these paths are stochastic, which means that, if I repeat the exercise, I'm going to get a different predictive for the first step, and then a different predictive for the second step, given the first. And so these are random paths. If I pick off the parameters after running this for 1,000 and I plot them, you get almost a perfect kind of histogram for the actual posterior distribution of the Bayes at time 0. So this is just telling you that if you run this through, you get back the classical Bayes approach. But let's look to more kind of general predictives, and a really interesting one is a non-parametric one. And I'm just going to take the empirical CDF. I'm going to take the empirical distribution function as my predictive. And so what does that look like? It says, well, here on the right-hand side is my empirical CDF. I've got atomic measure, I've got an atom at the observed data points. And my predictive at n+1 is just to choose one of the previous data points at random. Yeah, but remember, in this Bayes approach, we condition on that. We put that back in. So now that I draw an atom in this polyurn scheme, I then reinforce that atom by putting another atom on top of it. And I update this to 1 over n+1, and this sums from 1 to n+1, and I keep going. So this is a polyurn scheme with replacement and reinforcement. And we know that if you do that in the limit, you obtain a random measure which has these weights which are Dirichlet. And so people will instantly kind of recognize that what I'm showing here is the Bayesian bootstrap. So the Bayesian bootstrap of Rubin has this really nice predictive interpretation, which says you start off with the empirical CDF, you make a prediction, but then you update the empirical CDF. Yeah, in the classical bootstrap, there's no update. You draw n samples, IID, by conditioning on the predictive distribution. You never update the conditional. If you're Bayesian, that doesn't make any sense. If I've got a new observation, I condition on it. And you keep going in the limit, you'll get a random measure. And so we can look at, through this predictive lens, the difference between the Bayesian bootstrap and Efron's bootstrap. So here's Efron's bootstrap. I'll work through the right-hand side first. Take the empirical CDF, and then I want capital B bootstrap samples. I want to draw, because I'm frequentist, I want to draw data sets of size little n. So what I do is I sample a point from the empirical CDF, but I don't update the empirical CDF. I condition on that. It's like a hat on there. And then I generate another sample. I do that n times with replacement, but not reinforcement. And then I calculate my statistic of interest well, sorry, I get a data set of size little n, and then I calculate my statistic. And I do that b times, and there's my Bootstrap samples. The Bayesian Bootstrap predictively looks something quite similar, which is you start off from the same point, the empirical CDF. I've got b, I want b Bayesian samples. But here I'm now going to run from n+1 to infinity. The reason I want to go to infinity is I want to pick off the parameter of interest. This right-hand side tells me something about the finite sample variability of the estimator. I don't care about, if you're Bayesian, you don't care about the finite sample variability of the estimator. You care about the population parameter of interest. To do that, you need to give me infinite data. So we're going to sample a y from the predictive, but now we're going to condition on it, and we're going to update. And I'm going to keep going. Now, of course, I know mathematically I don't need to do this to infinity because I know what this thing looks like. But if you did run this, you then take a full data set and evaluate that parameter and repeat. And that would return you this. And that's the Bayesian Bootstrap. The Bayesian Bootstrap, of course, it means you don't need to do this kind of inner loop because you know what it's going to return. But it shows you the kind of, I think, contrast the differences. So I've said this too many times. You do predictive resampling, draw and condition, and then recover the parameter of interest. And the thing to note as well is you don't have to learn about a likelihood function. We can recover any parameter of interest using a loss function. And so here we're taking the random measure that comes from the imputed population, and we're picking off a statistic of interest that minimizes a loss function. And so the question is, can I use any predictive? You know, somebody says, oh, look, I've got an off-the-shelf model. It's a predictive model. Can I just plug this in and off we go, as long as I've got the update? Well, there are certain conditions that you would want. You know, if you're Bayesian, you're fine, but then you don't really need this if you're going to be doing standard Bayesian. So what are the conditions by which predictives, if I use this predictive imputation, that give you reasonable kind of properties? Well, the first thing you want is that you want the limit in predictive to converge to a random measure. So you get a probability. You get a probabilistic probability distribution on the parameter of interest. So we need for this to exist. We need this limiting distribution to exist. And the second property, which makes sense, is that you shouldn't be able to gain information by just predicting things that you haven't seen. And this kind of relates to a martingale type condition that says, you know, I'm predicting this data and I'm putting it back into the model, and I'm predicting data and putting it back into the model. If I repeat that, I shouldn't somehow be able to magic myself information from nowhere. And so that's a way of thinking about this martingale condition that says the expectation of this random measure given y1 to n should just be the predictive at yn+1. Of course, it has randomness, but the expectation of it should have this martingale condition. And that's essentially what Doob shows, is for within the classical Bayesian approach. So the second one is to show that it's sufficient that there's this martingale condition. And fortunately, sorry, for us, is that both of those conditions have been satisfied and have been studied in this really interesting work by Bertie and others on things called conditionally identically distributed measures or data. So this CID condition was introduced and studied in Bertie, and it has exactly the right properties that we want. And note that this is a weakening of exchangeability. Yeah, so this is a weaker condition, which allows us therefore to perhaps use more general models. So just to recap, we're going to impute from this joint predictive using this frequential factorization. And we're going to use if we use conditionally identically distributed predictives, then we know that this gives us a kind of has the right properties that we want, namely this martingale condition and the fact that we'll obtain a random measure. So it doesn't artificially introduce new information. And so we've now got three ways of building predictives. We've got the standard way, which is you take your Bayesian posterior and you get back Bayes. So it's an interesting viewpoint, but you haven't gained anything. We've shown that if you plug in the empirical distribution function as the predictive, you get back the Bayesian bootstrap, which is an interesting view. And now we're going to look at more general CID distributions, which gives us things we call these martingale posteriors. I'll move through a couple of examples quite quickly. I think it's interesting to think about what does this predictive inference look like for some very simple models like linear regression. So if you think back to how a classical kind of approach to linear regression in a conventional Bayesian setting says, oh, you assume that the data is normally distributed around a mean, and that mean has a kind of a linear format or a linear form on a set of covariates. But you're assuming that the model's true. Yeah, and then you're specifying a prior for the unknown parameters, the true sampling distribution. Yeah, and in the predictive approach, we don't have to assume that. So we can still think about a parameter of interest. And it's related to some recent kind of work, people thinking about, well, parametric models as functionals rather than as actual kind of true models. And so we think of this regression functional. And your task is to learn about this object. That's where I want to make inference about. And this is the parameter of theta, my model, that minimizes this kind of L2 loss. If we use the empirical CDF as a predictive, we get something that's very close to something called the weighted likelihood bootstrap and kind of recent extensions for being able to kind of do linear regression, Bayesian linear regression models without assuming it's true. Maybe the difference is in the weighted likelihood bootstrap. Newton and Rathfrey proposed this approach as an approximation, actually as a computational approximation to Bayes. We don't think about this as an approximation. We think about this as a valid form of Bayesian inference. It's non-parametric inference about this object here. Yeah, but this object here doesn't have to be linked to the notion of a true likelihood function. So we're going to use, here we use the empirical CDF to make the predictions, and then we pick off this parameter given a full population. The other kind of interesting thing to note is that if you construct the posterior in this way, it's got provably better properties than the Bayesian classical Bayesian linear regression if you're misspecified, and of course all models are misspecified. So if you're in M-open, if the model's wrong, building a Bayesian linear model using this approach is better in terms of frequencies coverage and predictive risk than using a standard Bayesian approach. So what we did is, here's an example. We've got a simple linear regression going here. We've got the true line in dark. And what we're doing is we're using effectively the Bayesian bootstrap, which is reweighting the data as if imputing ever larger data sets, and then picking off the least squares fit for this imputed population. So for every different population, you get a different optimal least squares fit, which can be solved using a maximization routine. And you just pick off those lines, and that gives you your posterior distribution, which is shown on the bottom right. And you get, usual kind of credible intervals. The other thing to note, just in the last 5 minutes, is we can also build kind of more interesting predictives by looking at this recursive update and relating it to some bivariate copulas. So it's worth noting you can kind of invert this, which is that all Bayesian models have a copula sequence, which says the predictive for I plus 1 at any point y is the predictive at iteration I times this rather horrible thing, and it's because we've inverted it to try and construct this. But this is a copula that's based on the predictive density at y, that's in here, plus the predictive density at the y I plus 1, which is drawn from this PI. So if you draw a value from PI, then you've got this copular update that gives you the new predictive. And this gives you a tractable sequence, which might not be exchangeable, but always satisfies the martingale condition. So if you build predictives using copulas, you're guaranteed not to add information into the future predictive, and that could that gives you the martingale condition that we need. And so we applied this to some kind of non-parametric kernel density estimation problems, where we're using a Gaussian copula that essentially says, oh, you make a prediction and then update the kernel density estimator using that prediction, and you keep going. And because the data generation is random, then the final density estimate, given a very, very large number of observations, will itself be random. And on the left-hand side, we're showing the kind of the copular update, which has a bandwidth, which is how much do you want to learn? It's a learning rate. Yeah, so if you're in M closed and if you're in Bayesian updating, you know how much to learn from each iteration. That's just given by the likelihood function. But if you're in M open, if the data is arriving outside of the model, there's a question of how much information does that contain for learning about the parameters of interest. And so in this setting, that comes down to a bandwidth in the copula. And essentially what it shows is we get very efficient inference for, in this case, one-dimensional, but also very high-dimensional density estimation, and it's also much quicker and runs in parallel. And there are examples in the paper. So I've got one slide for conclusion, which is we've looked at a predictive framework for Bayesian inference, and it treats the unknown, unobserved missing population as the source of the uncertainty. And the kind of tagline, I guess, is that you can think of all of Bayesian inference as a missing data problem. You think about the data that you need to answer the question and impute it. It emphasizes a close link between Bayesian inference and the ability to accurately simulate a system of interest. There's obviously very strong links with generative models here, and offers a potential way to objectivity because we know how to score predictive models. The other interesting thing is it makes clear the difference between frequentist uncertainty, which is take an estimator of interest and look at the finite sample variability given potential repeat experiments of size n, and Bayesian uncertainty, which can use exactly the same estimator, but where the uncertainty arises from the missing population. And if you plug in the missing population, then this indexes the true statistic, whereas this doesn't. This is why you get a confidence interval out of here and a credible interval on the unknown population parameter here. And I think there's interesting extensions over and above what we've done to use in modern kind of continual learning or online machine learning predictive modes for inference. And there's a accompanying paper if you're interested. And thank you for listening.